Alright, so we're going to cover 6.3, parts 3 and 4 today in this lesson, in which case part 3 is going to talk about the normal approximation to binomial distributions, and that is where we're going to talk about dealing with the 10% rule and our large counts condition. And these two are very important because those are going to come into play quite a bit in future lessons for sure, but the 10% rule, large counts condition. And then for part 4 of 6.3, we're going to go into talking about geometric distributions, in which case the only thing that changed, well, a couple things change here. And normally we talk about bins, and instead of having an n, now we're going to have a t. So we're not looking at the total number, now we're looking at the t is for the number of trials until success. And the mean is dealing with 1 over the probability. And the shape on these are always going to be skewed right. So unlike we're talking about in part 3 with approximately normal distribution, we're going to be talking about skewed right when we're dealing with geometric distributions. All right, so let's look at this, go through a problem. All right, so we're going to start out, like I said, with part 3 here, normal approximation of binomial distributions. So in a survey of 500 U.S. teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X equal the number of teens in a random sample of size 500 who have a debit card. Alright, so we got a lot of numbers here to throw out here, so let's see what we got to use. So with this one, we'll explain why X can be modeled by a binomial distribution, even though the sample was selected without replacement. So without replacement, so we know it's not really an independent, right? It's not independent because it tells us not a replacement. So let's look see what we can do. We'll start out here. So we start with our B, right? So we need for our success. So our success in this case is if they have a debit card. And then failure is if they have no debit card, right? Okay. So now we talked about our I in this case. For independent, we know it's not independent because we're not having replacement. So it could kind of depend on who's going to have one and who doesn't. So with this, it's not independent, but what we can use is one of our rules here that we talked about a second ago. So we can actually go into using the 10% rule. In other words, when taking a random sample of size n from a population, you can use a binomial of your sample size is less than 10% of your entire population. So that's what's talking about, 10% rule. So 10%, less than 10% of your entire population. Well, I guarantee you 500 U.S. teenagers is less than 10% of the population. Let's say of all U.S. teenagers. Okay, so that's less than 10%. So therefore, we can still move forward with this. So now n, for our sample size, what we had, it said sample size of 500. So n equals 500. And then for our last thing, our S here, for same probability, right? Well, the probability, suppose that exactly 12% of teens is telling us that. So probably 12% of teens have debit cards. So have debit cards. So probability is 0.12. So with that, these check out now. Even though it wasn't independent, because it's less than 10% of the population, we're able to move forward with that. So number 2 here, it says use a binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. Well, to do this, we're going to want to use a Binomial Cdf. So Binomial Cdf. Now in this, of course, you're going to need to put some numbers here. To start out with this, I'm going to say if we use the TI inspire, so say inspire here, so one of two ways. So this inspire, move this over a little bit. If we were to go to menu and statistics, distributions, I should be able to scroll down a little bit. Oh, there it is, sorry, a little too far. Binomial CDF. So in here, the number of trials is 500. Click over here on it. 500. Our probability was 0.12. Lower bound was 0, and our upper bound was 50. So therefore, we should come out to get a 0.093 what we use for this. Now in this, you need to label what you have, just like in the calculator. So for this, we had our sample size of 500. We had our probability of 0.12, our lower, and our max, in which case, well, min and max, I should say. So we have our sample size, have your probability, have your min, and your max. And that came out to be 0.093. Let me write that 93 a little bit better. 93. That's if you have the inspire. It's easy to calculate that way. If you need to use, what's it called? Desmos. The Desmos calculator. Let's go there and see what we got. So here in the Desmos calculator, you should be able to go to functions and build it binomial distribution. In which case, I want you to put the trials and the success probability. So we had 500, and the probability was 0.12. And then you want to click on Find Cumulative Probability. Our min was 0, and our max was up to 50. And as you can see there, it gives us 0.093 as well. So the Desmos calculator can work on this as well. So it was labeled binomial distribution. So in this case, they called it binomial distribution. And again, they want us to set up 500 trials, and probability was 0.12. Okay, and then you had to set up your min was 0. Your max was 50, and we still came out to a 0.093. Okay, so in other words, a probability that 50 or fewer teens sample have credit cards, or debit cards, sorry. So there's 9.3% chance that 50 or fewer teens in the sample have debit cards. Okay. All right, let's see what we got to do next with this. So now it says justify why x can be approximated by a normal distribution. Well, it can be approximated by, we're going to use this little rule here for the large counts condition and see if it works. So therefore, if this works, we can use a normal distribution to model a binomial if your n times p, so your sample size times your probability, is greater than or equal to 10, and the sample size times 1 minus your probability is greater than or equal to 10. So let's see what we got here. So again, we're going to want to find first, we're going to say n p is greater than or equal to 10. Well, our sample size was 500. Our probability was 0.12. I don't know why you want to put 1.5. 1.2. I want to say that's greater than or equal to 10. Well, this should come out to give you 60, which is greater than or equal to 10. So that checks off. And then you write n times 1 minus p. That's greater than or equal to 10 as well. And we got 500 times 0.88. See, that's greater than or equal to 10. And therefore, we should come out to 440 is greater than or equal to 10. So that checks off as well. Now, when you're checking this rule, you need to label these and list them out like this. Now, granted, you don't have to put the base formula up here, but these are needed. That's needed. That's needed. And then your check mark showing that you understand that that works out. Those are needed to be able to justify large counts, okay? Have to write those out if you're asking a problem. I think there's one more problem here for this example. Let's see. So we got using normal distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. So with this, we're wanting to look at normal curve, right? We said it'd be approximate normal based on our large counts. So we know the mean we set up here is what would we say? Well, our mean is going to be our n times our p, right? So like we just did a minute ago, we took 500 times our probability of 0.12, and that gave us 60. So now our mean is at 60, all right? And we're trying to look at 50 or fewer. So we're going to look somewhere over here. Just going to draw a line here. We're going to call that 50. And 50 or fewer. So we're wanting to shade this area. This is very important too. If you can show your graph in shade, that's the best thing. If you understand how the problem is read out, make sure to draw the little graph. It's key points. What are we missing on this normal curve though? You need to label it with what it is. So in this case, we also need to find out what our standard deviation is. So how do we find our standard deviation? Well, to find out our standard deviation, we use that equation that we dealt with by saying a square root of n times p is 1 minus p. So we would simply take square root of 500 times 0.12 times 0.88. A horrible 8. Let me draw those. Read them easy. 8. And that should come out to give us 7.27. So we're missing out our little normal curve here. Then our 60 is our mean, and our standard deviation is 7.27. All right, we've checked that off. Now, to do this, since we have these values and we're trying to find the area under the curve, we need to find our z-score. So your z-score is x minus the mean divided by the standard deviation. Well, we have all those values except for our z. So we can definitely find that out by saying 50 minus 60 over 7.27. So therefore, our z-score is going to equal negative 1.38. So in other words, what it's saying is the z-score is 0 here, and this is negative 1.38 for the value of 50. So we can simply go into doing our normal CDF or normal distribution, and we'll just go ahead and do that in in Desmos. So in Desmos calculator, do the normal distribution. Okay, let's see what we got. So we'll do our function here. Well, let's go ahead and enter here on this one so we can get to the next problem. function, and we want to do normal distribution. And for this, we're going to go from our mean, which in this case was 0 and 1, 0, 1, and then our min is from negative infinity up to, we had negative 1.38, in which case we should come out to get 0.08, we'll say 0.084. Okay. 0.084. Again, we went from our lower bound, it's negative infinity, to negative 1.38. We had 0 and 1. Sorry, I kind of ran out of room here. So our lower bound, upper bound, mean, and standard deviation. And that gave us 0.084. So the area under the curve is 0.084, or you say 8.4%. Either one of those is correct. And that's what you're looking at for those, okay? So that's dealing with 6.3 part 3, dealing with your 10% rule and your large counts. And then we did a little recap here on actually solving for a z-score and using our mean and standard deviation for these as well, and finding the area under the curve. All right, so let's jump into part 4. So again, part 4, we're going to be talking about the geometric distributions. We're going to deal with the bits and how our mean and shape, how those are different. So let's look at this. All right, so Marty decides to keep placing a $1 bet on number 15 in consecutive spins Marty decides to keep placing a $1 bet on number 15 in consecutive spins of a roulette wheel until she wins. On any spin, oh my goodness, start over. Marty decides to keep placing a $1 bet on number 15 in consecutive spins of a roulette wheel until she wins. On any spin, there is a 1 in 38 chance that the ball will land in the 15 slot. Let T equal the number of spins it takes until Marty wins. All right, so show T is the geometric random variable. So with this one, again, we're dealing with bits, the BITS. So our B, we're going to say success is she wins, right? And if her failure is lose. For our I, if this is independent, well, the spins are independent, right? Doesn't matter what she spins on one spin to the next spin. So the spins are independent. Now we're looking at T, right? Instead of an N, we're looking at T for the number of trials. So this is just talking about the number of trials. So the number of trials until Marty wins. So until she wins. And then we have to look at the probability. So a probability, right? So with this one, it has the same probability for every time she spins, right? There is a 1 in 38 chance of that happening. That's the probability. So that equals our probability. So no, that's all good. We know we've got a geometric random variable. Again, to determine this, of course, is just the actual setup between geometric and using the bins is dealing with, this is talking about until she wins instead of giving a set amount of trials, okay? So again, this is not giving a set amount of trials as we're using the T value instead of an N where we had a set number of trials, okay? So for number 2 here, it says find the probability of T equals 3 and interpret the results. So for the probability of t to equal 3, excuse me, we're simply going to work out here saying we have, she's going to have to say lose, lose, and win then, right? For interpret to actually find the probability of t equals 3 for the third try to win, right? So she would take a lose, and a win. But what's the probability for those? Well, lose, she has a 37 out of 38 chance of losing, right? Because there's a 1 in 38 chance of winning. And I had 2 of those. And a win, 1 in 38. So in other words, it's saying the probability that her third try she wins. So in other words, you take a lose, and the third one she wins. So you have a 37 over 38 chance for each one of the loses and a 1 out of 38 chance she wins. And we're just going to multiply these together. Okay? And that should come out to give you a 0.025. So to interpret that, we're simply saying there is a 2.5% probability that Marty wins for the first time on the third spin. So again, there is a 2.5% probability that Marty wins for the first time on the third spin. All right, so let's see what we got. So how many spins do you expect it to take for Marty to win? So what do you think it would take for her to win if she has a 1 in 38 chance? Well, if the world was perfect, it should take her 38 spins as the expected value, right? Expected value is 38 spins. Because there is a 1 in 38 chance of her winning. So, therefore, you should think that, well, if she spins at will 38 times, she should win. So 38 spins is expected value. And would you be surprised if Marty won in 3 or fewer spins? And compute an appropriate probability to support your answer. So with this, we're going to have to use a geometric CDF, right? Because we're looking at the probability of the trials being less than or equal to 3. And to determine that, we would take the geometric CDF. In which case, I cannot find that on Desmos, so I'm going to show you how this works on the TI Inspire, right? So on the TI Inspire, we would simply go to our menu, 6, distributions, there it is, geometric CDF. All right, so it wants to know the probability for success. Well, we said that she has a 1 in 38 chance of success. And our lower bound, of course, is, say, 1. And we definitely want to go to 3. Because we want 3 or fewer. Click OK. And therefore, we get 0.077. So again, with this, it wanted us to put in the probability and the min and the max. Okay, so the probability for this was 1 out of 38. Our min was 1. Our max was 3. So probability, min, max. That came out to a 0.077. So, would you be surprised if she won in 3 or fewer spins? Well, I wouldn't. The reason why is I would say no. No, because winning in 3 or fewer spins has a probability of 0.077, which is not that rare. Why do I say it's not that rare? Because we can pair these probabilities to 0.05, 5%, right? And because that is greater than 5%, it is not that rare. So it could happen. It wouldn't surprise me. She could win in 3 or fewer spins based off that probability. Alright guys, so that goes into talking about normal distributions for binomial distributions, approximately normal distributions for binomials, and geometric distributions as well, and how they're a little bit different. Again, big thing is understanding your 10% rule, large counts, and for geometric, understanding that the number of trials is what changes from actually having a set number of trials. In this case, for geometric, there isn't just trying to find a number of trials until success. All right, so hope you learned a little bit something today, guys. I'll see you next time.